Friends, welcome to this lesson on peripheral interface devices. Most of the microprocessor applications will have at least two things in common. That is, they'll be reading data from an external device and writing data into another external device. Consider the case of an electronic weighing machine. The CPU in such a machine will read data from the A to D converter and write data into a display device. Of course, in any such application involving interfacing between CPU and peripherals, you can use discrete devices. This was covered in an earlier lesson. However, a better approach would be to use a special circuit designed for this purpose. Such special circuits are called peripheral interface devices. They are available in IC form. They have an advantage, that is, they can be programmed to do a variety of interfacing functions. The Intel 8255 is one such peripheral interface device. It can be used with the Intel 8085 CPU. So in this lesson, we are going to learn about the details of 8255. The device features three numbers of ports named A, B and C. Each one of them is an 8-bit port. However, port C can be divided into two 4-bit ports and used separately. The device also has an 8-bit internal register to store the control word. The control word is used to configure the three ports of the device either as input or as output. The lines A0 and A1 are used to address the three ports and the control word register. The read bar and write bar lines allow the CPU to read or write into the device. The data lines D0 to D7 are connected to the data bus of the microprocessor. The chip select signal enables the device. The operation of the ports can be classified into two broad groups, the I/O mode and the bit set reset mode. Under I/O mode, the device offers three specific modes: mode 0, mode 1 and mode 2. Under mode 0, the port A can be set as either input or output port. In the same way, the port B can also be set for input or output operation. However, there is a flexibility in port C. It can be divided into two 4-bit ports, the C lower and the C upper. Each of them can be set independently for input or output operation. The mode 0 is also known as simple I/O mode. Under mode 1, the port A or B can be set for input or output operation. The bits from port C are used as control signals. These control signals are used for handshaking. The mode 1 is also known as handshake mode. In mode 2, the port A is used as a bidirectional port with port C for handshake. The mode 2 is also known as bidirectional mode. Bit set reset mode makes use of only port C. Any bit of port C can be set or reset. So we have learnt about the interfacing details. Now let us go on to learn a simple application. The application involves interfacing switches at a port and interfacing LEDs at another port. The application is designed to operate in I/O mapped I/O mode. Therefore, the read bar and write bar inputs of the device are connected to the I/O read bar or I/O write bar control signals. The address decoder is designed so that the chip is selected for the I/O addresses 20, 21, 22 and 23. Port A is configured for input and port B for output. Let us study how to frame the control word for this configuration. The 8 bits of the control word completely configure the device. Each bit encodes certain detail about the operational mode. Port A and upper half of port C are grouped together and called group A. Port B and lower port C form group B. Group A can operate in mode 0, mode 1 and mode 2. While group B can operate only in mode 0 and mode 1. The bit D7 chooses between I/O mode or bit set reset mode. When it is 1, I/O mode is selected. When it is 0, bit set reset mode is selected. The bits D6 and D5 determine the I/O mode of group A. Since group A can be operated in mode 0, mode 1 and mode 2, the 2 bits are needed to select the mode of operation. The bit D4 sets the port A for input or output function. When it is 1, the port A becomes input port. When it is 0, the port A becomes output port. The bit D3 sets the port C upper for input or output. The bit D2 determines the I/O mode of group B. The bit D1 sets port B for input or output. The bit D0 sets the port C lower for input or output. Since I/O mode is being set, the bit D7 is made 1. The group A has to be operated in simple I/O, so the bits D6 and D5 are made 0, 0. Since port A has to be input port, D4 is made 1. Port C is not used. Therefore, D3 can be 0 or 1. Group B has to work in simple I/O mode. Therefore, bit D2 is 0. Port B has to be output port, so D1 is made 0. Port C is not used, therefore D0 is made 0 or 1. So, for our application, the control word works out to 1001 0000, that is 90H. So the first step in doing this application is to load the control word. So this process is known as programming the device. It's also known as initializing the device. But how do we load the control word? The application is designed to operate in I/O mapped I/O mode. Therefore, the out instruction can be used to load the control word into the control register. Let us now move on to the graphics to learn about the steps in programming the device. The 8255 in this application is designed to operate in I/O mapped I/O mode. The I/O address of the control word register is 23H. The move immediate instruction loads the control word into the accumulator of the CPU. The out instruction transfers the control word to the control word register at address 23H. After these instructions are executed, the device is programmed. Port A will now operate as input port and port B as output port. The switches connected to PA3, PA4 and PA6 are closed. The rest are open. The status of the switch data can be transferred to the LEDs by writing into port B. The I/O address of the port A is 20 and port B is 21. The in instruction reads the port A data into the accumulator. The accumulator content becomes 01011000. The out instruction puts this data into port B. When these instructions are executed, the LEDs connected to PB3, PB4 and PB6 become on. The LEDs which glow now correspond to the switches that are closed. Mode 0 is the most widely used mode of 8255. It finds many common applications. Consider the case of traffic lights. The ports of 8255 can be made to switch on and off the different colored signals with a given time delay. Mode 0 is ideally suited for this application. Again, consider washing machine. The 8255 can be made to read different parameters such as water temperature and water level, and it can be made to switch on and off relays and pumps. Again, mode 0 is very much suited for this application. Having learned the details of 8255, let us view a demonstration in which external devices are connected to 8255. The external devices connected are LEDs and switches. The 8 switches are connected to port A and the 8 red LEDs are connected to port B. The port A is operated in input mode and the port B is operated in output mode. The device is operated under mode 0. A program is executed which will switch on the LEDs one by one in sequence. Go 8800, execute. The program uses delay routines and a rotate instruction. Another program is demonstrated which reads the status of the switches and displays the status on LEDs. When I switch on this, nothing happens. That is because the switches and LEDs are not under the program control. Now the program is executed. Go 8C00, execute. Now if I turn on any switch, the corresponding LED glows. If I switch it off, then the LED is put off. This shows that the switches are red and the status is immediately transferred to the corresponding LED port. Before we learn mode 1, let us learn about the bit set reset mode. Under bit set reset mode, any of the bits of port C can be made 0 or 1. So this is particularly useful in a situation where we have to selectively switch on or off a bit. Let us go to the graphics to learn the bit set reset mode in detail. In bit set reset mode, any bit of the port C can be set or reset. The D7 bit is to select IO mode or bit set reset mode. When it is 0, it selects the bit set reset mode. The bits D6, D5 and D4 are not used. Port C has 8 bits. Any one of them can be set or reset. The 3 bits D3, D2 and D1 select any one of these 8 bits. For example, to select PC4, D3, D2 and D1 will be 1, 0, 0. The selected bit is set when D0 is 1. It is reset when D0 is 0. Therefore, to set PC4, the control word works out to 09H. The move instruction loads 09 into accumulator. The out instruction transfers it to the control word register. It is now time to learn the details of mode 1. Consider a typical peripheral which will have a mode 1 interface with the CPU, that is the printer. The printer is an electromechanical device. Its printing speed is much lower than the working speed of the CPU. Therefore, though the printer can receive data at any rate from the CPU, its printing speed is much slower. So, the data transfer between the printer and CPU proceeds something like this. The printer has a buffer, memory buffer within it. So first, the CPU sends a byte of data to the printer. The printer receives the data, stores in its buffer. Then it sends an acknowledgement back to the CPU. Then the CPU sends one more byte to the printer. This process repeats until the buffer is full. When the buffer is just full, the printer stops sending the acknowledgement. The CPU also stops sending the data. Now the printer proceeds to print its entire buffer content. Once its buffer content is over, it again starts sending the acknowledgement. So this process of data transfer is known as handshake method of data transfer. This has an advantage. The CPU need not be wasting its time waiting for the printer. So meanwhile, it can be doing certain other task. Now let us go on to learn the details of mode 1. Under mode 1, let us study how port A can be used as an input port, and certain bits of the port C will be used as control signal for this purpose. Bit 4 of port C is used as the strobe input. Bit 5 of port C is used as input buffer full signal. Bit 3 is used as the interrupt signal. The port A may be connected to a peripheral which need to be interfaced. The peripheral, when ready with a byte of data, places it on port A. Then it puts a 0 at the strobe input. In response to this, the 8255 raises the input buffer full signal. The 8255 also raises the interrupt signal. This interrupt can be made to interrupt the CPU so that the CPU reads the data by placing a low on the read bar signal. The read bar signal resets the interrupt and input buffer full signals. Now 8255 is ready to read another byte of data. So that was input operation under mode 1. Now let us learn output port operation under mode 1. The port B may be used as an output port. Bit 2 of port C is used as output buffer full signal. Bit 1 of port C is used as acknowledge signal. Bit 0 of port C is used as interrupt request signal. Port B may be connected to a peripheral. Output buffer full and acknowledge signals are also connected to the peripheral. When the CPU is ready with a byte of data, it writes into port B. In response, the 8255 lowers its output buffer full signal. The peripheral, sensing this, reads data from port B. After reading, it lowers the acknowledge signal. After receiving the acknowledge signal, the 8255 raises the interrupt request signal. This interrupt may be used to get the next byte from the CPU. So now we have learned the details of mode 0 and mode 1. Let us apply these to interface a complex device, that is an A to D converter. An A to D converter requires a trigger signal called convert start to start the conversion. The conversion immediately begins, and after a small time delay, the digital data is ready. The CPU can read the data. The A to D converter indicates this by a signal called end of conversion. Therefore, the data transfer between the A to D converter and CPU not only involves the digital data but also the start conversion and the end of conversion. Therefore, a mode 1 operation is called for. In addition, certain A to D converters requires an address information to select one of the many channels that are available. This calls for operation in mode 0. Now let us move on to the graphics to interface the A to D converter 0808. In this application, port A is operated in mode 1 and port B is operated in mode 0. Port A is used to read data from the A to D converter. Port B is used to address the channels in the A to D converter and to start the conversion. The 0808 can take in 8 analog channels. To select any one of them, the device needs a 3-bit address. For example, to select channel 0, the address is 000. First, this address is put out through the bits PB2, PB1 and PB0. This address is latched into the A to D converter by sending out a 1 on PB3. After this, the conversion is triggered by putting a 1 on PB4. The conversion now begins. The A to D converter indicates the end of conversion by raising the end of conversion signal. The end of conversion signal is latched. The inverted output of the delatch is applied as strobe input to IC 8255. The input buffer full signal resets this strobe input. The cycle is again started by applying a new start conversion pulse. Now let us review what we have learned in this lesson. The 8255 is a peripheral interface device which can be programmed. It offers 3 8-bit ports to the user. Programming is done by writing the control word into the control word register. It offers IO mode and bit set reset mode. Under IO mode, simple input-output interfacing as well as handshake data transfer is possible. Bit set reset mode is good for manipulating individual bits of data. We have also learnt simple application like interfacing switches and LEDs, and also a complex application like interfacing an A to D converter. So we can conclude that 8255 is a versatile interface device to be used with the Intel 8085 CPU.